This is Machine Learning Platform at Flipkart, Agility with Scale by Nikhil and Sudhir.
So hi, I'm Nikhil. I run the machine learning platform team at Flipkart. Co-presenting with me today is Sudhir, who is an architect at Flipkart.
Double XL, I guess.
So big picture, right? What we are going to cover is the what, the how, and the why, which is why do you need a machine learning platform? How do you go about building it? How do you go about using it? That kind of stuff, right? So in order to motivate, I guess, the need for a machine learning platform, let me take you guys back to 2006. So in 2006, Netflix started the so-called Netflix prize or the Netflix, challenge as such, right? At that point in time, Netflix was pretty much a different kind of business, or at least a different delivery model. So you went to Netflix and you picked a few movies that you liked, and based on that, they shipped you a few, or based on that, they showed you recommendations. And based on these recommendations, you picked a few movies, and they shipped you the DVD via mail. You watched the movie, you rated the movie. So basically, it took somewhere around 3-4 days for you to get a DVD for the movie you picked, right? So recommending movies to people was important. I mean, it was important for them to be able to really identify what movies a particular user would like based on algorithms like collaborative filtering. And they collected a lot of data over a period of years, and they decided to do this thing wherein they put out a large training set, they had a blind set, people pretty much submitted their predictions, and basically the way the prize was set up was, the metric was RMSE, and basically they wanted to get a 10% improvement over the baseline, which was in production. And they had a prize of around $50,000 for a yearly improvement. And then they had this large prize for somebody who achieved a 10% improvement over the baseline, right? So there were, this started in 2006. Let's say 2007, there was a progress prize, 2008. In 2009, this team, that's Belcore Pragmatic Chaos, finally achieved that 10% improvement over the baseline and won the $1 million, right? That's the dashboard. It's a snapshot of that. And they actually were handed the prize, right? Now, if you guys already know about the Netflix prize and how it turned out later on, don't raise your hands. But how many of you think this model went into production? Show of hands. By production, I mean making predictions in production. No? Nobody thinks it went into production? Wow. I mean, you probably know about this then. So this is a direct quote from their engineering blog. And basically, the model did not justify the engineering effort around it. And that's interesting because $1 million was given out in a prize. Clearly, more expenditure would have gone in making all this operational. But the model really didn't go to production. So there were a few learnings along the way. But the fact that it didn't go to production should raise some red flags for people in the machine learning community, right, as such. And the reasons for this, the cited reasons for this, and I should give the entire background around this, the delivery model also changed, right? So Netflix went from shipping people DVDs to having movies streamed. So basically, you don't need to be that accurate if you get your predictions wrong. The user can just go away if he doesn't like the movie. But the 2 points to take note of here is A, the model which was given $1 million in prize, didn't go to production. Second, the business changed, the tech stack changed, and because of that, people ran into trouble, right? So I guess what I would like to do next is really talk about um, where do data scientists or an entire data science team that is in the business of shipping out a model that will make predictions in production, where do they spend their time? I mean, you have a fair amount of time in the problem definition, you have some amount of time around data set generation, some amount, I mean, a very little amount of time is actually spent in modeling, and then a bulk of time actually goes into like reproducing the model at prediction time, integration with production systems, making the features that were used during training available at production time, so on and so forth, right? So for the, for a lack of a better word, just let's refer to this as the plumbing around the model, which takes a much more effort in terms of time, as well as, it just pushes your deliverables much further down. Secondly, what happens is you have to sometimes just go revisit the problem definition, because certain features that you depended on to build the model were not really available in production, right? So this is based on my experience, my diaries over at Flipkart, bunch of data science projects, as well as a couple of organizations in the past. So where would we like to be? I mean, where will we want to be at a place where we are spending the bulk of time doing the modeling and the evaluation, while the rest of the stuff, while it is an overhead, is kept to a bare minimum, right? We would like to be here, but what we are is here. So I guess the key takeaway here is more time and resources are currently both in a startup setting, I would say even at an enterprise setting, across the board, is spent doing the plumbing around the machine learning model rather than the actual machine learning model, right? So that's a reality. Now, well, how do you, how are people approaching this? I mean, how are teams organizing themselves around machine learning, right? One of the standard approaches, it's a little like the waterfall model that we used to have in software engineering, is the throw it over the wall approach, right? So basically what you have is, you have a bunch of data scientists who are going to extract their data, build their models with their favorite tools, and they are going to pretty much hand over POC code, MATLAB, R, Python, whatever, right? They're going to hand over the POC code to developers, who are then going to integrate that or rewrite that into the production systems, which is then handed over to DevOps, who will basically just go ahead and deploy it, right? So this is a little waterfallish, and it is definitely not agile, in the sense that, let's say, to give you a specific example of how business can be impacted, the entire demonetization meant that people are going to cancel the orders that were cash on delivery, because they don't have cash anymore. Now, if I could use a model that got somebody's credit rating right, and just send them an email that, hey, pay me later, pay me 1 month down the line, I could go ahead and reduce my cancellations by a big chunk, right? So in that particular setting, I would need to have such a model built pretty fast, or I would have to retrofit an existing model or whatever, right? But the point is, in this kind of a throw it over the wall approach, your time to production for a particular model is pretty much, it's so high that you cannot really use this unless, of course, it's a very well-caged problem that just is going to have very slow incremental development, right? So definitely not agile, definitely not, workable. The alternative, and this is a little agile, as it's called, is wherein, the feature team approach. So what do? You take a data scientist, you take a developer, you take a DevOps, at least one each. You put them together as a feature team, and it would be their job to go ahead and take a model and productionize it end to end. So what these people are going to do is, they would have enough domain expertise, they would have enough development as well as deployment expertise within the team, and they'll be able to take this specific model across the board. So this is another way in which people approach, I would say, the delivery around machine learning, right? Now the problem with this approach is, how many feature teams are going to have? For a large organizations, let's say like Flipkart, if you have 100 models, you are going to have a team of, you're going to need 300 people to do this, right? Secondly, just because a model has gone into production doesn't really mean that you don't have to maintain it. The features are going to, change over time. You are going to have to analyze the drift. You're going to have to make these changes to your models, and it has to be maintained in production. So this entire feature team approach doesn't scale. And by scale, I mean with scale with the number of people. You'll just have to throw too many people at the problem in order to, if you go with either, or if with that approaches. So take home point is, again, can we really be agile with scale, right? And I guess this is where we come to the whole idea of the ML platform. And some of the key ideas here are, basically a data scientist has a limited set of tools. They use these tools to build models, and they are able to independently take these models to production using the ML platform. Right? So basically, the ML platform integrates with your production systems and is maintained by developers and DevOps. But basically, data scientists are able to basically innovate and implement models, evaluate them, take them to production end to end without really needing to needing to work with anybody else. They are basically in self-serve mode. Now, this might sound a little science fiction-y. It's not. It's pretty straightforward. But this can be done. I mean, my claim is, and I can demonstrate it, that this can be done on a budget. This can actually be done with a fairly small team by making the right choices in terms of what you choose to implement, when you choose to implement it, just getting the whole design right? So, I mean, the key idea here is basically that you need an ML platform if you really need to make your data scientists productive. The entire data science narrative is, if you have data, if you hire data scientists, they'll solve your problems, aka profit, right? But my claim is, it doesn't really work that way. It doesn't work that way because a lot of models don't go to production. And this can be a solution, and it has worked pretty well for us so far, right? So let me start by, now go into the little bit of, the how, as to, what are the key learnings that we have had? What are the key design principles, design patterns, if you want to call them? How do you get your basics right so as to build this on a budget, right? So I would say the first design pattern is really separating the model training from the model prediction. So for instance, let's say I'm building a model in scikit-learn, Python, right? I should be able to implement, or fairly easily, these components like exporter and predictor, which allow me to take the representation of the model and put it in a format which can be interpreted by another entity, right? So for instance, and this should contain pretty much everything that takes you from the input features to the output features that is ML specific. So basically, let's take a very simplistic model. I have a few input features. I do some normalization, one-hot encoding, feature selection, followed by a random forest, right? That leads to an output. Now, this could be trained here and needs to be predicted here, but it's fairly easy to implement such exporters and predictors and really externalize the model from your, so basically you have completely now segregated your training pipeline from your production or prediction pipeline by implementing these two components. Now, the question is, has this been done before? This seems very simplistic. Yeah, this has been done before, but not really well. For instance, PMML, which was a XML-based format to really achieve this. But it's big, it's bloated, it didn't have enough exporters and predictors, and basically it didn't have support for all the other peripherals around the model, right? So it wouldn't have some of these things, and then typically people would end up in implementing their own formats. Or it wouldn't have enough predictors for Python, they had for R, it's not there for C++, blah, blah, blah. So although the people have tried to standardize this hasn't really worked that well. But my claim is that for a particular set of use cases, implementing exporters and predictors is very, very possible, right? You have to determine which ones you need, and we'll talk about that later down the line. But I guess the most important lesson here is you have to segregate the model training from the model prediction, right? Now, then the question becomes, which exporters and predictors do you choose to implement, right? What we have here is pretty much the tyranny of the tech stacks. You have data scientists with their favorite tools, which are complete ecosystems, right? Python, R, MATLAB, rich set of tools that people have used throughout their grad schools, continue to use them, are very productive with them. And on the other hand, you have your production systems, which might be Java or C++ or something else, but you basically have this issue of, really having to choose or really having to deal with at least two tech stacks. And multiple things have been tried out here and haven't worked. So for instance, there are, I guess the startup that I worked at pretty much decided to do everything that they do just in Python, so that it would be very easy to productionize models. I have also seen teams who say that, hey, because it'll become so easy to productionize, let's just do everything in Java. But the fact of the matter is, except that these two are separate you are going to need at least two tech stacks, right? Now, you might decide to choose some, right? You'll have to choose at least two, but try to eliminate as much as possible, right? So, for instance, like at Flipkart, I would say most of our ecosystems production systems are based on the JVM. Our data scientists are by and large comfortable with Python. That's what I would choose. Perhaps if I was working in high frequency finance, I would probably go with R and C++. Depends, but the key take-home point here is, if you want to implement the right set of exporters and predictors, you do want to limit your tech stacks, but accept that there will be two, right? That you are going to need two specific tech stacks. So that's a key learning, right? Moving on. Let me talk about the particular set of algorithms or models that you would decide to implement exporters and predictors for. And my claim here is less is more. What you need and what you want are there's a big difference between the two. So let's start looking at what kind of what kind of algorithms, what kind of implementations or models do you need to attack a lot of business cases. And what we see here is, when it comes to, let's say, training data, let's just talk about how big are my training data sets. And I basically, here on the x-axis I have the size of the training data, and on the y-axis I have the number of business use cases. So this is pretty much true at Flipkart. It's true, I would say, across the industry, that for a large number of business cases actually just have to deal with small amount of data. I guess and this is going to drop down, right? There are going to be business use cases that are going to deal with a huge amount of data, but those are few. A lot of problems or a lot of business use cases can be tackled just with, the data sets aren't that big, right? And turns out you could address this with a single big memory machine. So for instance, getting a terabyte of RAM on a bare metal in Flipkart is very easy. You can do that, get that machine and probably solve problems really fast. If that doesn't work for you, if your data sets are larger, you could go, set up a Spark cluster. If that doesn't work for you, you're going to need parameter server and friends, right? But my point is, you need to figure out what you really need. How big are your data sets, and what are the different business use cases? I know it's fashionable to, say big data, but the point is your data really big, and what are the business use cases you're handling, right? So something to keep in mind. So basically, should I go implement exporters and predictors for parameter server or Spark first, or should I just go support something based on scikit-learn, which can help out in most of the business use cases? So that's an important question, right? The second one is, how many algorithms and models do you need to add business value? So it turns out, by implementing just a few, you are you can cover a lot of business use cases. Random forest, support vector machines, gradient boosted trees, basic stuff that will allow you to cover a lot of business use cases until you need really sophisticated or specific implementations. That's going to happen much later, right? So again, less is more. Figure out what you need in terms of which algorithms, which particular models you need, and you will be able to restrict the scope, right? So, and it's important to build for immediate value and then mature the offering, as and when you need it, right? So let me now come to basically the key components for, of the ML platform, which allow you to build really, I would say, if, build models effectively and have them in production in a scalable kind of a way. We spoke about exporters and predictors before. A few other components you're going to need are things like a model repository, which is basically Git for models. You're going to need a dataset repository, which allows you to store and version control data. You're going to need a feature factory, which is basically a feature repository as well as it procures data in real time or by hitting an API, right? And these three things together, joined by a metrics service, is a very broad perspective on our architecture. But the key ideas here is your data pipelines, might evolve over time. People might move from Hive to Spark. Your data scientist workbench might change from Python today to R tomorrow. Your production systems are changing all the time. But pretty much all you have to do, and this is why I said this can be done over a budget, is implement new exporters and predictors as and when required. This entire ecosystem is pretty much the same. So once you have built these components and then you incrementally improve or add to these, you're all set. And you can, over a period of time, mature this entire system to support a bunch of different algorithms, which would definitely allow your data scientists to just, have a library implementation, use the exporter, go to the model repository, and on your production system, somebody will just pull the model, use the features, and make predictions. So that's our overall architecture, and what this also allows you to do is get to doing metrics properly. I mean, are my models being reproduced properly? Am I seeing a feature drift? So on and so forth, right? So that's our overall architecture, and again, the key the key takeaway here is you should bootstrap your ML process by building these 5 components. You could build them on a budget before you actually start them. Something around ML or something around modeling. So now I suppose we'll go into more nitty-gritties and implementation details, and I'll just hand over to Sudhir. Yeah.
Hey, let's look at some of the common use cases in our organization for machine learning models. So there's a user insights team wants to start predicting the age of the user. They would want to work on a new model, right? Some of the models may already be existing in production. You may want to upgrade them. So for example, you may want to retrain the model for gender prediction with using updated label sets. You may want to replace the model using the same set of features, right? So these are backward compatible because you don't need to work on the pipelines for feature generation and other things. You just have to put in, productionize your model and it works. There could also be cases where your changes are not backward compatible. For example, your new model may actually need new features. So you have to work on the pipelines, generate the features which are needed and make changes in production. There could be changes in your data pipelines itself, where you're moving from batch to streaming, right? Or even the definition of the features are changing. There could be changes in your production systems. Today you are doing an offline evaluation, you may want to do it an online evaluation tomorrow going forward. For example, fraud, doing a batch versus online makes a lot of difference, right? So the machine learning platform we built tries to simplify these scenarios by helping quickly build, deploy, and iterate the machine learning models at scale. So let's look at the use cases. The first thing which a data scientist, when he starts working on the problem, is he identifies a list of features which he would like to give as input to his model and see how they perform. So he comes up with a wish list of features. Features are something like, I need total orders which the user has played for a particular store, how many times did he cancel, what places did he use to browse, what is the gender of the user. There could be a number of features as input. Right, so we have this feature repository which Nikhil talked about. So as and when people keep adding features to this, it will grow over time. And so most of the features can be reused. For example, the number of times a user places an order is something which could be improved to consumer finance, RTO, fraud cases and other use cases. Right? So if you don't find it in the feature repository, the data engineer has to work on building the pipelines to get the data into the system. He may use batch or streaming of his choice and build the data. Once the data is generated in the way the data scientist wants, you may want to do, for the training purpose, pick a subset of the data and push it to a dataset repository. So this acts as a reproducibility for the data scientist. So he can keep playing around with the same data set with different models, and he can look at the performance of the models. And when he's happy with the performance, he may push it live. Right? So he will push it to the model repository. So he may use the tools of his choice, like Nikhil was saying, Spark or Python. And he can use the exporter to go and push it to the model repository. Now, your production systems you may want to run this prediction in your own system. So you may have an API use case, right? Or you may have a batch use case where you're running at a MapReduce job or Spark streaming, some of the streaming topologies, right? If you want it embedded in your system, you can use the predictor library from the machine learning platform, run it integrated with your framework. It's a thin, lightweight library, and you can predict it at runtime in your system. You may choose not to have this in your library. You may want to have a hosted service. So we have a hosted prediction service. All you have to do is get the features from the feature repository, give it to the hosted prediction service. The model details are there. You end up predicting it, right? So this while you are getting the features, some of the features may not be in the feature repository. It may as well be at some other system. For example, in your MySQL database or in your some other backend system serving the data at runtime, because they may also be changing, right? So we have this feature extractor component which needs to understand like how do I get this feature from other system. It could be a web service, it could be a database lookup, it could be edge-based lookup, it could be actually talking to the feature repository and get those features, right? So if you look at this, we have simplified the productionizing problem, we have simplified the dataset generation problem. But even now, if the features don't exist, you spend a lot of time in generating the features. So we built a platform for feature generation to simplify this problem. In a normal case, your data goes to your data warehouse. Your data warehouse. So you have your Hive jobs which generate facts out of it, or you'll have MapReduce jobs which generate the data in the form you want to have, and you will push it to the feature repository, right? So, but there are use cases like recommendations or fraud detection where you want the data to be updated in near real time. For example, the moment a user has placed an order, cancelled an order, is doing some kind of fraud, you want to is blacklisted, you want that data to be updated in near real time. Batch doesn't work in this case. So we focus on building this near real time framework where the moment an event comes in, the features are updated in near real time in the repository. Right? An example of these features, like I was saying, the common use cases are how many times is the user ordered. But it is not just that. These guys, the data scientists will be interested in the time partitions also. You may say, I need the order counts in the last 3 months, the last 6 months. Some may say, I need the last 1 year browse visits of the guy. They may say, I want in a particular store, how many times did he order, right? Category of a product, right? There could be different pivots on these. And if you see most of these features, what we have seen is are easily aggregatable. So like order counts, if you count an order for a day, you take 7 days orders, you can always say this is the order count for a week. Similarly, if you take 30 days orders, you can always say this is 1 month orders, right? Clear? So most of the features are aggregatable in our case. So we built this framework keeping this time partition also as a framework there. So all the user has to do with this is define, this is the type of the event, this is the type of the feature which is generated, and this is my business logic on how do I convert this event to this feature, right? In this case, if you're getting a browse event for a user, let's say it has lat longs, right? And you want to resolve it to a pin code. You will say this is the pin code of the user, this is the user ID, and this is the count from where he has ordered this many times. Is it clear? And along with it, you define on what granularity of time do you want to maintain this. You will say, I need the counts on a daily basis, weekly basis, monthly basis, historical basis, and the platform takes care of generating it. So the way it happens is our data platform team gets events ingested in near real time by external systems, the producers, which is basically the front-end teams or the order processing systems. They also have the capability of joining events in a stream using Cassandra and Storm topologies. So we are reusing that framework to join multiple events. In our case, we get order details in a separate event and the order placement in a separate event. So we want to join them and get enriched event together. There could be other enrichments like we want to enrich product ID information to price and other details. So we get these into our Kafka. And we are using Spark streaming because of 2 reasons. One is we want the same code for bootstrapping also to work in a batch use case. And Spark streaming kind of suits it well. And also has integration with a lot of, it supports micro-batching, and we need micro-batching support in our case. Because the user may be browsing a lot of times in a small window, a few minutes or seconds. We don't want to recompute it so often for them. So a few seconds of batch windows is acceptable by us. So once we get these events, we do external lookups. We enrich it. For example, look lat long. I was saying lat long to pin codes, and then we publish it to the feature repository. the features, as I said, are aggregatable. So we could, if you want to say, you got an order event, you want to count the number of times the user plays an order, you'll have to get us current orders, add it, and then put it back, right? So this getting and putting it has race conditions, or you'll have to get all the data for user to a single node. So we are using edge-based coprocessors to do it at the server side, where these operations of aggregates happen on the server as a service instead of the client getting it. So we are increasing the parallelism and increasing the throughput of the system. All you have to do is tell the edge base, go and do this aggregate operation on this user, this dimension records. Right, so now your features are all updated in near real time, or could also be updated by a batch process. Now let's say you want to take an action also along with it in near real time, where if a user has placed an order, you want to trigger your recommendation model, or you want to trigger your fraud detection model. So the feature updation information is also sent to the features Kafka, from where you could be listening to n number of features like order events, browse events, cancellation events, and then you could say, I need to compute this model. So this guy contacts the model repository, gets the models, contacts the features repository, get the features. You evaluate the model, you predict the model, and then you publish it to your consumer Kafka. This all can happen near real time. Today we are running it in under 2 minutes of an activity of the user on his device. We are able to push it out to the consumer. That includes the lag in the data pipelines and all. So this is how the sample job config looks like. We define saying what topics you want to listen on. This is the feature generation part, the first phase. You define what topics you want. You define your event, how it looks like. This is the schema of the event. In this case, it is a browse event. You have the account ID, you have the IP address, user agent, other fields. And then you have the feature of the user. So we define annotated with saying this is a user ID, which is an account ID in this case. This is the dimensions on which you want to do group by, where in this case it is a store path, which means that for a user and a particular store, I need the counts of how many times did he visit, right? And we also want to see when did he first come to the store, when did he last come to the store, right? And along with it, you define saying that I'm interested in these time partitions. I want daily, weekly, monthly, and historical time partitions for this kind of data. And you define the map function to convert this browse event to this browse count signal for that particular event. And this platform takes care of generating it for all these time partitions, and does the aggregate and pushes to HBase. This is how simple it is. And the second part of it, we also simplify the feature extraction. All you have to say is, these are the topics, these are the features I'm interested in for any updates. You define on what are the durations of frequency, duration of these features you are interested in. Like you are interested in 6 months of browse counts, 3 months of order counts, 3 months of order store path counts. And this framework takes care of extracting out for that granularity and gives it to the system. And you can run your prediction logic in this consumer. Right, so now you have your data in your feature repository. Now the data scientist needs a data set. So from the feature repository, you can read the data, and using one of your choices like Java or Python SDKs, which we have supported, you can create a Spark data frame or a Python Pandas data frame and publish it to the dataset repository. With each publishing, you create a unique identifier and a version associated with it, and you share that with your data scientist. Now the data scientist uses this to train his model, and once he's happy with the model, he can publish it to the model repository. So the model repository basically consists of your metadata of the model, like who has created it, for what purpose, who is the owner, and some additional details. And using the predictor functions, using the export function of the libraries, you can push it to the model repository. This is how simple it is. So along with this, you specify the version of the model. So you say, what is the change in this model? Are your features changing? If it is not, you're just retraining it with the same features, but updated labels, you say this is the release version has been updated. If you're actually changing the parameters of the model, or the algorithm is changing, you say this is a minor version upgrade. If you're saying this is the features itself are changing, then you say this is a major version upgrade. So this is just the information telling to the system that this is the change in the model. And in the production systems, you will load this model, and you using the predictor library, you transform this and get the prediction out of it. This is how simple it is. Now your production system may say, I don't care about the release version. As long as I'm getting the features, I will give it as input to the model, and I need to evaluate it. right? So you can always specify a minor version or a major version and say, I don't care about what upgrades are happening in the model, let the data scientists worry. So the developer no longer needs to do any code changes. As long as his framework supports dynamic loading of the models, it works, right? And we can have an A/B service or metrics at the back end where the data scientist can keep tweaking those parameters and himself control the platform and make it work. So the key takeaways from this session, which we want to conclude, is basically you understand that today the real problem is data scientist is not getting enough time on model training and evaluation. That is where we should be spending most of our time. You need an ML platform to do innovation at scale, right? You have to understand that data scientists and developers will have disparity in tech stacks, and it is better to segregate the training from predictions. So reduce the number of algorithms, reduce the number of platforms which you want to support so that you can focus on the things which are more important for the business. You build the key components, dataset repository, model repository, metric service, prediction, and exporters, and that helps in quickly productionizing your model. Along with it, you need to simplify your feature generation, because the faster you can experiment, the data scientist can experiment, the better it is, right? So the go live time for a model from begin to end reduces a lot using these approaches. That's it. Any questions? We'll be happy to answer. Sure. Nikhil, you want to come?
So I have built a model. Using R, I have built a model, right? So now intention is to productionize it, right? So my concern is, after a couple of days when the model is live, because of that new incremental data, my model performance might decrease, right? So do we have any feature? So do we have any feature in this analytic platform where with the data, n numbers of model can be iterative, and based on that
Yes.
new way we can.
Yes.
So if you look at this metrics service, right, the idea behind this is to measure three specific things. One is the faithful reproduction with a blind set. The other is live side metrics, which is basically, is the model performing or making the same kind of predictions, or little technical, but basically I can compare the distribution of the input features over a moving window. So basically, let's say before and after demonetization, did my RTO or cancellations go up or down? And that, if I'm using as a feature somewhere else, I would
Will
know.
it do model comparison? That is what I'm asking.
Yes,
Different
yes,
models.
yes. That's
Either
the
logistic
trivial part.
regression or random
Yes.
forest, and based on that, it will give me the best output.
Yes.
Okay. Now with the incremental data, logistic is giving better result compared to random forest. But previously, random forest was best for me. So that is what.
So that is the intention of the metrics platform. So it will give you comparison between different versions of the model,
Exactly.
and you can compare and choose what you want. It is not going to automatically determine.
Okay.
At some
based
point,
on
you
the-
may build that intelligence, but right now it should be like you decide on how much A/B should you give, what parameters to tweak, and
So did you mean for A/B, or did you mean for on a blind set? So, I mean, my point is, let's say you have a particular problem for which you have a training set and a blind set. On that training set, you have published 5 models, and that you're evaluating on a blind set, which might be updating by a data pipeline. Is that what you're talking about? Or two models are live, and some amount of traffic is going to both, and I'm looking at that
second part
the
what
second
you-
one.
yeah.
No, I think integration with AB service is something external to the ML platform. Of course, you could use the hosted service and drive traffic this way or the either, but we don't really tightly integrate with the AB service. It's at the client end that this determination will be made.
in a short answer, yes, you can do it.
You okay? All right.
Yeah. Somebody there.
So as you told, for aggregatable features, you use HBase and basically aggregate the features, right? How do you handle non-aggregatable features?
You can do it via batch process. You can go and do it. So anyway, non-aggregate via streaming is anyway difficult, and it's not performant enough at scale. So you will end up doing it in batch. Today we haven't seen that.
That support is there already?
There's nothing stopping you from doing batch, right? You can write your own custom code. As the streaming pipeline, we don't handle that. The assumption for the streaming pipeline, it's all aggregatable. Sure. Yes, yes.
Let me take that actually. So, okay, so specifically, right, it's the data engineer who is going to build the data pipelines to publish data sets as well as feature repository specs in these two places. So as soon as the data pipeline is modified, you will be able to propagate these changes to a dataset repository. So to be very specific, let's say there is a new feature which can be procured by hitting a REST API that is also available as a part of your data platform. It's there, and it's also here. So I would say yes, there is a touch point between the data engineer and the data scientist in which the data scientist would say that I need you to update your data pipeline for my data set to have a new column. Yes, that does slow us down a bit, but I would say that in the interest of reproducibility, that's a price well worth paid, because I mean, while it is very much possible for a data scientist to quickly log in and get the data and then put it in his data frame, we would like the pipeline to evolve with it. And actually, I mean, this is not what you asked, but let me say this. I mean, our belief is that there are only so many features that would be required in an enterprise setting like Flipkart. I mean, maybe 5,000, maybe 10,000, but eventually as we keep building these, I mean, as the feature repository grows over a period of time, you could just go and use existing features to, get the agility.
Okay, you mentioned that in one of the previous company you tried to implement everything using Python. So what has been your learning there?
Well, Python is very close to heart, so it's hard saying the challenges about Python publicly, but I will. So the thing is, I ran into heavy issues around concurrency, heavy issues basically around maintaining large code bases. We ended up in implementing some core aspects of our I would say production systems in C++, and then I mean, Python just remained as a layer on top. So I would say definitely issues around concurrency and issues around maintainability were the two things. So I mean, when it comes to scale, I would say using the JVM, I mean, that would have been a wiser choice. But yeah.
So, can you just comment about some offerings from competitors like Amazon or Azure ML versus something which might be in open source, like a lot of work which is happening around in Berkeley?
Sure. So, okay, let me talk about Amazon's machine learning API. Basically, they give a end-to-end, I would say, offering in terms of store your data sets on S3, use elastic MapReduce to build your models or whatever. There is also the machine learning API wherein you would be able to wire up your, I would say, data sets from S3, build a model, and again make it available via REST API. But two parts there. One, you have to be on AWS entirely. Second, the only mode of making predictions is via hitting a REST API. I mean, typically at least at Flipkart, we need 4 modes. There is batch, wherein I need to run a MapReduce job or a Hive query. There is streaming, something like Storm or Spark streaming. There is hosted, wherein I need to hit a REST API. And then there is embedded, wherein you cannot afford to make an API call over the wire to a machine. So they just support hosted, and you have to be on AWS. So that's about Amazon. With Google, I suppose the prediction API, I mean, they not only want to eliminate the engineer in the process, it seems that they want to eliminate even the data scientist in the process, which is cool. But my point is, basically, it's really throw data at it and magic will happen kind of an offering, I would say, at least the prediction API. Right? I mean, you don't have as much control over the hyperparameters, even in some cases, what algorithm you're using. you're basically throwing data at a black box, and then the black box knows best, right? So yeah. So those are the two. Yeah.
Yeah, the Spark thing. Yeah. So on this,
I would say, yeah. Let me talk about Spark a bit. ML lib in Spark. I would say Spark, by and large, it's a great effort. They're going to go ahead and add a bunch of algorithms. Their algorithmic offerings are maturing over time. But again, it's a very closed ecosystem in the sense that they expect you to make predictions also in Spark. So this idea that a data scientist has his own Spark cluster, has many good implementations of algorithms, they build a model, and if they were making predictions on their own cluster, it would work out perfectly. But turns out that we want to train somewhere and then predict elsewhere. And that support of getting the model out of the ecosystem to go make predictions elsewhere, I haven't seen a very mature offering around that. And I suspect, given these are academics or whatever, take a new data set, build a model, publish results. It's also used in the industry, but this problem that we have of, we need to build models somewhere and we need to use them somewhere else is not something they're directly attacking.
Next question gets a slash and coffee mug. You guys need to pick up the